Hello, my name is Liu Yinjie, CST2509025. Today I'm going to talk about my project titled Convolution and Data Processes under the broader theme Applications of Linear Systems in Science and Engineering. In this presentation, I will walk you through three main ideas. What vector spaces mean in this context, how images can be presented as vectors, and how concepts like subspaces, bases, and PCA help us process images efficiently. The first is what vector spaces mean in this context. When we talk about linear systems in image processing, the idea of the vector space becomes essential. A vector space is simply a collection of objects called vectors that can be added and scaled while still staying inside the same collection. In our context, these factors don't have to be arrows or geometrical objects. They can also represent data, such as pixel values of an image, sound waves, or sensor readings. This means many scientific and engineering problems can be described using linear algebra tools, which makes them easier to analyze and compute. The second one is how images can be represented as vectors. An image is basically a grid of numbers. Each pixel has an intensity value. And if we take all those values and place them one after another, we can form a long vector. For example, a 100 multiply 100 grayscale image contains 10,000 pixels. So we can think of it as a vector in a 10,000 dimensional vector space. Why do this? Because once images become vectors, we can apply linear operations like convolution, filtering, compression, and recognition using the same mathematical tool we use for vectors in linear algebra. The third is main section, vector spaces, subspaces, and bases in image processing. Now let's go a bit deeper by looking at three related ideas. Uh, what is a vector space? A vector space is a structured environment where vectors can be added and scaled smoothly and predictably. It comes with a set of rules, such as having a zero vector, additive inverses, and distributive properties that ensure everything behaves consistently. This structure allows us to model complicated systems using simple linear relationships. A vector space includes a set of vectors, a field of scalars, and two operations, vector addition and scalar multiplication. But more importantly, it includes subspaces, smaller vector spaces inside the big one. These subspaces often capture important patterns or features in data. In image processing, these subspaces can represent things like lighting variations, facial features, or texture. The last one is what can vector space do? Vector spaces allow us to find structure inside huge amounts of data. A perfect example is PCA, Principal Component Analysis. In PCA, we treat a collection of images as points in a high-dimensional vector space. PCA then searches for the directions, called basis vectors, that capture the most variation among these images. These basis factors form a new coordinate system that highlights the important features. This is exactly how eigenfaces work in face recognition. Each face image is expressed as a combination of several basis faces. When a new image appears, the system checks how it fits into this subspace. By using fewer dimensions, we compress the data while keeping the essential features. This is where mathematical elegance meets practical efficiency. To sum up, vector spaces are not just abstract mathematical ideas. They provide the foundation for representing images, analyzing patterns, and performing tasks like compression and recognition. Through tools like PCA and interfaces, we can transform large complex image datasets into smaller, meaningful subspaces that preserve the key information. That's all for my part. Thanks for your listening.
Example, blending and linear algebra in image processing. Blending combines visual information from two or more images, often used in photo editing. augmented reality, and multimedia. In mathematical terms, blending can be understood as a linear combination of pixel values, which naturally connects to the concepts of vector spaces and linear transformations. Image processing as vector space operations. In image processing, every image is treated as a vector in a high-dimensional space, with each pixel representing a coordinate. This perspective allows us to apply powerful linear algebra techniques for compression, enhancement, and recognition. Subspaces and bases. By identifying meaningful subspaces within the image space, we can represent images more efficiently. Principal component analysis is a classic method that finds a new set of basis vectors, the principal components that capture the maximal variance in the dataset. These basis vectors form a lower dimensional subspace where images can be approximated with minimal loss of information. Eigenfaces example. In facial recognition, PCA gives rise to eigenfaces. Each eigenface is a basis vector representing a fundamental facial pattern. Any face image can be expressed as a linear combination of these eigenfaces. Recognition is performed by projecting a new face into the subspace and measuring its reconstruction error. This approach reduces storage, speeds up computation, and enhances robustness against noise. Image filtering and enhancement. Operations like sharpening, blurring, edge detection, and noise reduction are implemented using linear transformations. A filter is represented as a matrix that convolves with the image matrix. This process is essentially a matrix vector multiplication in the vector space representation, transforming the image according to desired visual effects. Image compression, singular value decomposition, SVD, factorizes an image matrix into three matrices, allowing compression by obtaining only the largest singular values and their corresponding vectors. This low-rank approximation preserves the most visually significant features while drastically reducing file size. SVD is fundamental in formats like JPG and in algorithms used for image recovery and denoising, image recognition, and machine learning. Modern AI and computer vision systems are deeply rooted in linear algebra. Convolutional neural networks apply layered filters through matrix convolutions to extract hierarchical features. Dimensionality reduction techniques project images into meaningful subspaces for clustering and classification, support vector machines, and other classifiers often operate in high-dimensional feature spaces derived from images. In each case, vector spaces provide the structural foundation, enabling efficient computation, theoretical analysis, and practical implementation.
Hello, Professor. My name is Li Jiatan, and my number is CST2509021. Let's look at another examples. When you are taking photos on your phone, have you ever used a sharpen, blur, or edge detection filter? Or have you ever wondered how AI is able to recognize faces? Behind all of these functions lies a single core mathematical tool, and that is convolution. This slide, so let's look at these three examples. This slide visually demonstrates the concept of two-dimensional convolution. It shows how applying mathematical operations between an input image and a small matrix, which is called a kernel, results in a new output image. But first of all, we need to understand actually the input image is also a very big matrix because every pixel in this image can be represented by a red, blue, and green, which is three different numbers. So let's look at the first examples, which is sharpen filter. We input an image of creepy, and then we input a sharpen kernel, which is designed to enhance the difference between a pixel and its neighbors. So we can output a clear, sharper image of creepy with more defined edges. And the second is blur. We input an image of Mario and a mean blur kernel. In this case, all values are 9 times smaller than it is before. So we can output a blurred image of Mario. This happens because each new pixel's value is the average of all pixels in its 3 times 3 neighborhoods. With which smooths out all sharp details. And then for the third example, actually we can use filter to do whatever you want. So let's define the positive is blue and negative is red. We can input an image of pi symbol and we input a kernel which is designed to detect horizontal edges. Notice the negative values on top and positive values on the bottom. At last, we can output an image that retains only the horizontal edge features of pi symbol. This proves we can design kernels to extract any feature we want. So now we have understand what filter can do for us. But to really understand it, what it is, we need to catch a glimpse of its process. To filtering, the first step we're going to do is performing a 180 degrees rotation on the kernel. This step is usually skipped in the data processing because the kernel can be stored in already rotated form. Then we slide in the kernel on the whole data such as matrix of pixel. Each time we slide the element on the kernel multiply the corresponding elements in the data. Then result of multiplication is accumulated to be the result of the position which correspond to the central elements of the kernel. So today we have talked about vector space allow us to represent image mathematically and linear algebra operations that help us to multiply, compress, and understand them. And whether it's PCA, SVD, or neural networks, the foundation is the same, the language of vectors and metrics, and what we are going to do when we are taking photos, which is filter. So next time you edit or filter a photo, remind you are actually walking inside a massive vector space. That's all for today's discussion. Thank you for your attendance.